For this next lesson, 6.2 of the 214 part of the course, we're going to discuss rational and irrational numbers. And to start this off, we're going to start out with going back to our A's. And the question asks us, show how you could add 1/2 plus 1/3 using an egg carton. So I'm going to start out with 2 egg cartons. I have 2 egg cartons, one here and one here. And I'm going to look at this carton and take out half of my eggs. So I'll remove half of my eggs because that's half of an egg carton. And since there were 12 eggs originally, half a carton is 6 eggs. And then for 1/3, I'm going to go back. Remember, we had 2/3 of our eggs before, but now I'm going to take out 2/3. And here I'm left with 4 eggs or 1/3. So what I'm going to do is I'm going to consolidate all my eggs in one egg carton. So here I took out that 1/3 and I added it to my 1/2 to fill up my egg carton here. So it counts how many eggs do I have now. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 eggs. But it's in an egg carton with 12 slots. So my denominator is 12 for the total number of slots in my egg carton. And then my numerator or top number is 10 for the total number of eggs that it's filling up. Now I want to reduce this, and in order to reduce this, well, I see that 2 goes into both of these, and 2 goes into 10 5 times, and 2 goes into 12 6 times, and that's my final answer. So that is how I would add 1/2 plus 1/3 will give me 5/6, and that's adding using egg cartons. In example number 2, we're asked to add 3/4 plus 1/2. And we're asked to do this again using egg cartons. So we have to look at it. We're going to start out with 2 egg cartons and see how much, and do the same thing we did before. Now, in order to get 3/4, we have to take our first egg carton, and we're going to divide our first egg carton into 4 pieces. And we're going to take out 1/4. So here, so this is a 4th, this is a 4th, this is a 4th, this is a 4th. So each 4th consists of 3 eggs. So I'm going to take out a 4th from one of my egg cartons. So there's my, so I'm left with 3/4 filled, and then 1/4 is empty. Now I'm going to take my other egg carton, because I'm going to add that together, and I'm going to take my other egg carton, And I'm going to take out 6 of them because that's half of a carton until I'm left with half of a carton filled. So now I have 3/4 of an egg carton filled, and I have 1/2 of an egg carton filled. So now what I want to do is fill up as much as I can because I'm adding it together. So I'm going to take some eggs from here and fill up my whole carton here. So I have 1 full egg carton. So that will give me equal to 1. And then the ones that are left over, I put into this egg carton. And I'll put it like this. So there's my filled egg carton. I'll put it aside and I'll write 1 for my full egg carton. And now I have only 3 eggs in this carton. So that leaves me with 3/12. And then I can reduce 3/12. And that is equal to 1, because 3 goes into 3 1 time, and 3 goes into 12 4 times, and that gives me 1/4, 1/4, so I have 1 whole egg carton filled, and only 1/4 of my second egg carton filled. So again, I have my first egg carton now is all filled with eggs. So I have a full dozen, and then my second egg carton is only filled 1/4 filled with eggs. In example number 3, we're going to show how multiplication is a form of repeated addition. So we're going to look at the situation of 2 times 3.5. And in this case, we're going to use a similar analogy as our eggs, and we're going to make stars. So I'm going to go 3.5 stars. So I have 1, 2, 3, and I call this one, there's half of the star. And then I do 3.5 stars again. 1, 2, 3, and then I'm going to draw half a star. And there's my half a star. So I have 2 rows here. They're the same thing. And it's 2 times. So here I have 2, 1 row, 2 rows, and each of the rows has 3.5 stars. So that means if I add up my stars, I get 1, 2, 3, 4, 5, 6, and then 2 halves make 7. So that means I end up with 7, a total of 7 whole stars. So these 3 are whole stars, but when I put these 2 together, I will get a whole star. That'll make 7. Okay, so we're going to discuss the sets of real numbers. And real numbers are broken up down into parts. Now often, and maybe in the past you've seen this, what's called the real number line. And that's a number line that looks like this and has little ticks in it for 1, 2, 3, 4, 5, 6, and -1, -2, -2, -3, -4, etc. Now, the thing is that part of this line from 1 on are the numbers we're most familiar with, and those numbers are the natural numbers. So we can indicate those numbers as 1, 2, 3, 4, or sometimes we call them the counting numbers. And these are the natural numbers or counting numbers. And these are indicated by the symbol N with 2 bars. Now, if we add in 0 to this, I'll make this a little clearer. If we add in 0 to this, we're going to get what's called the whole numbers. So if we put 0, 1, 2, 3, 4, ... and the 3 dots means it goes on and on forever, we will get the whole numbers. And this is indicated by the symbol Z with a little plus. So if I was going to, here are the natural numbers, I'll put these as the natural numbers. And then I'll put here the whole numbers, where that includes 0, whole numbers. And this is the whole numbers. Okay, so those are our whole numbers. And then we want to include on this number line, we also want to include our negative numbers, because we now have the 0 and the whole 0 with the natural numbers, but we're still missing this part, and that will be our and those will be what we call the integers. So here are the integers. So from here, which would include all of these, both the positive and the negative numbers, and these are the integers. So the integers are the set with 0, 1, 2, 3, 4, which are our whole and natural numbers, but also include -1, -2, etc. So that means it goes all the way smaller and smaller and smaller in the negative world, and yet it goes bigger and bigger and bigger in the positive world, and we call these the integers. Integers, which is just Z with a line through it, and so this is going to be our integers, which is just plain Z, where this is just the positive part of Z. And Z, why Z? Well, that's Zahlen in German, and N, natural numbers, and then the Zahlen with the plus means it's just the positive side of the integers. Now you may ask what other kind of numbers can be in this, because we're not finished. We still haven't covered all the real numbers. Well, there's also fractions, because in between here we have, let's say, 1/2 over here, and then 1/4 over here. We have fractions. And the fractions are what's called rational numbers. So any number, A over B, is an element of what's called the rational numbers Q. So any fraction is where you can put A over B. So even if you have one of these numbers, 4 you can write as 4 over 1, which means that it is a rational number. But so is 1/2 a rational number too. So any number that you can write as A over B is equal to a rational number. And a rational number, as I just wrote, the symbol for rational numbers is Q. But we're still not finished. That will cover everything. So rational numbers will be everything, not just the integers, but all of the numbers that we can write A over B in between. But we're still not finished with the real numbers. We're still looking for the set of real numbers. So we completed our natural numbers, our whole numbers, our integers, which I just accidentally erased, our integers, and our rational numbers, which is all the fractions in between. But we're still not finished. So there's another kind of number that is also part of this, which is called the irrational numbers. And irrational numbers include numbers like pi, square root of 2. So here we have that irrational number, square root of 2. And it's irrational because it is not terminating. So we see it goes on and on and on. And we cannot have any, we do not see any repeated pattern. So no matter how far out we bring this ... there'll be no real clearly repeated pattern. Another very famous irrational number is pi. And everybody's heard of pi, I would think. And if I put pi into my calculator, because my calculator, it turns out, has a symbol for pi. So I'm going to press the symbol for pi and see what comes up. And here I have, so here's my pi. Okay, get my pi here, equals pi equals, and here I have 3.14159265336, and this basically goes on and on and on. This is as much as my window tells me, and my window may or may not be rounding that off, because the last number usually on your calculator could be a round off. Okay, so as we see, this does not terminate, and nor is there any clear-cut pattern. And there have been many mathematicians who have tried for years and centuries to see if there is a pattern here, and have brought it out to the millionth decimal places and on and on and on, and still no one has found a pattern, nor has found that it terminates. And this is what happens with irrational numbers. Irrational numbers you cannot put into the form of A over B, which either terminates or is repeated. And that's rational. Rational implies these are irrational, which does not do this. As mentioned earlier, not all numbers are rational. So, for example, the square root of 2 cannot be written as a quotient of two integers, meaning A over B. So if we did that, if we took went to a calculator and put in the square root of 2, we would find that the number after the decimal does not have any pattern, and nor does it terminate. And this tells us that it's most likely irrational. So an irrational number is not rational, and is not rational, and is the set. So this becomes the set of irrational numbers, and this is pi is an irrational number, square root of 2 is an irrational number, and psi that we talked about earlier when we were talking about the golden ratio is also an irrational number. So let's try to see what it may look like on a number line. So square root of 2, we can say falls somewhere around here on the number line, but it's really, really hard to put it exactly on a number line, but this is about where square root of 2 is. Now, the way we would derive square root of 2, or how it comes about, is by using the Pythagorean theorem. Now, the Pythagorean theorem we'll learn a little bit more about later on, but that tells us that a squared, meaning one side, times b squared, another side, is equal to this long side, c squared. So we calculate that out, and we see if we use this as a unit and this is a unit, 1 plus 1 is the square root of x squared, and then because 1 squared and 1 squared is 1, and that becomes the square root of 2. Another irrational number is pi. And pi, it turns out, is the diameter of a circle, is the denominator, and the circumference of the circle is the numerator. So it would be the circumference divided by the diameter. And no matter what circle we get, we always get 3.14159, and then a whole bunch of numbers that are all very, very different. And many mathematicians for years and years and years have tried to bring it out to the billionth and the trillionth and the quadrillionth decimal, and have found that and no mathematician has yet found a pattern where there's some kind of repetition or termination. And as mentioned, no matter how big or how small the circle is, the relationship of the circumference divided by the diameter is always 3.14, or pi. So now we know all the components of the real numbers. So we started out with the natural numbers, or counting numbers, and which was 1, 2, 3, 4, 5, etc. And then we added on 0 to get the whole numbers. And then we put in the integers with the negative numbers. And then we put the rational, which is all the fractions. And then we now have the irrationals, and these are all the components and some examples of a few irrational numbers, including psi we talked about as the golden ratio, and these are some irrational numbers, and all of these numbers make up the real numbers. And we will explore this a little bit more in greater detail in 6.3. So thank you very, very much, and stay well, and until the next time, take care. Bye.